Hiya both. Well, not long to go now for the end of this term. So we're trying to get through De Moivre's theorem by the end of the next couple of weeks. This is the second video on De Moivre's theorem. The first one was me introducing it, showing you the proof by induction, and then a couple of simple examples of using it that were to do with raising complex numbers to powers and using De Moivre's theorem as a sort of a shortcut to finding out the results. We're going to be doing more on that after this little mini section of De Moivre's theorem, which is to do with trigonometric identities. So you'll recall what these are. These are basically identities between trigonometric functions. For example, cos squared theta plus sine squared theta is always equal to 1, and sine 2 theta equals 2 sine theta cos theta, etc, etc, etc. There are loads of these. Well, we can actually use De Moivre's theorem to establish some really important trig identities that can then be used in other areas of maths. It's quite cool the way this works. So I'm going to go through what it explains in the FP2 textbook, and then you can read it for yourselves, and hopefully between reading that and listening to me, you'll kind of get the gist of how this all hangs together. So basically there are two types of trigonometric identity that we're going to be able to prove or show are true using De Moivre's theorem. The first ones, the easier ones, are the ones where we find a way of writing cos n theta or sine n theta or tan n theta in terms of powers of cos theta, sine theta or tan theta respectively. So if we're doing cos theta, we'll write it in powers of cos theta, sine we'll write in powers of sine theta, and tan we'll write in powers of tan. Now, just give you an example of what I mean by this. You already know, and you will have used this result in polar coordinates, although not actually in this form, that cos 2 theta is actually equal to cos squared theta minus sine squared theta. Actually, I lied. You have used it in the correct form. I'll explain what I mean in a minute. So you've got cos squared theta minus sine squared theta. If I replace sine squared with 1 minus cos squared, using another well-known identity, then I end up with 2 cos squared theta minus 1. And what I have just done is I have, take that bit of it there, I have written cos n theta in terms of cos theta, powers of cos theta. So this is a cos squared theta term, this is a cos to the 0 theta term, something like that, I suppose you could say. Anyway, you get the idea. So what on earth has this got to do with De Moivre's theorem? Well, I'll show you. So this is the example in the book. I'm just basically doing what they do. Okay, so suppose you've got cos 3 theta, and you want to write that in terms of cos theta, effectively. What you do is you start off by writing cos theta plus I sine theta cubed, like that. Cos theta plus I sine theta cubed, like that. And then, because of De Moivre's theorem that I wrote at the top of the page, that is the same as cos 3 theta plus I sine 3 theta. So we've used De Moivre's theorem to get a link between cos n theta and indirectly sine n theta, but this is the one we're interested in, and cos theta and sine theta raised to a power. So what I need to do now is to multiply this bracket out. And I'm going to do that using the binomial expansion. Because it's only cubed, I could have done it, anyway. But you know, this could be on the next question, this could be a 7. I could be trying to find cos 7 theta in terms of powers of cos theta. So I'm actually going to expand this bracket. So here we go. So 1331 is the Pascal's triangle line, so it's going to be 1 times that cubed, and then 3 times that squared times that, and then it's going to be 3 times cos theta times, and then I'm going to raise the power of that by 1, so it's going to be I sine theta squared. Notice I'm not doing any cancelling down at this stage, I'm writing the thing out. Okay, and then finally it's going to be 1 lot of that cubed, so it's going to be I sine theta cubed, like that. And then all I do now is I have a little fiddle with that, make it look a bit nicer. So I get cos cubed theta. So I'm sorry, I should just clarify, I'm just writing that out here. I should really set it equal to that, but I've run out of space, so I'm not going to. So cos cubed theta, so this term here is going to be 3I sine theta cos squared theta. Now this term here has got an I in it, but it's going to disappear because it's I squared, so it's going to become minus 1. So it's actually going to be minus, and then I'm going to get 3 cos theta sine squared theta. And then my last term is going to be, well, it's going to be I cubed, so it's going to be minus I. It's going to be minus I sine cubed theta. Like so. And I end up with 4 terms, 2 of which don't have an I in them and 2 of which do. And it's the ones without the I's in them that I'm interested in, because what I do now, I wish I had a different colour on me, but I haven't, is I compare all of that with all of that. And these 2 things are the same. And so if I equate the real parts, I'll have cos 3 theta is equal to cos cubed theta minus 3 cos theta sine squared theta, like that. Okay. Now I'm trying to write cos 3 theta in terms of just cos theta, so I need to do a little bit of fiddling here. I basically need to do something with this here. Using the identity, the standard identity that sine squared plus cos squared equals 1, I can rewrite that as 1 minus cos squared theta, like that. Okay, and now if I multiply out the bracket, I'll get cos cubed theta minus 4, sorry, plus 4, get it right, 4, I'm going mad. It's going to be plus 3 cos cubed theta, that's that times that, I don't know why I'm doing it in the wrong order here, and then minus 3 cos theta, that times that. Which, if I simplify, becomes 4 cos to the power 3 theta minus 3 cos theta, like that. So that is what cos 3 theta is equal to. If I want to find sine 3 theta, I don't have to do a completely new question. I can use the same result, only this time I would equate the imaginaries rather. I'm not going to do it because it's one of the questions in the exercise, but I would equate the imaginaries rather than the real. So I would say that I sine 3 theta is equal to that term and that term. And once again, I'd have to deal with this cos squared theta term here by rewriting that as 1 minus sine squared. But it amounts to the same thing, and I'd end up with an expression for sine 3 theta in terms of powers of sine theta. Okay. So that is one of the applications of De Moivre's theorem. Oh, you can do tan theta as well, and I could explain it to you now, but I don't want to make the video too long. You can read it for yourself. Okay, if you the example is tan 4 theta. Now I'll just tell you, to do tan 4 theta, you you basically do sine 4 theta and cos 4 theta separately. Well, I say separately, they're done in the same way as this, but with a power of 4 here. Okay, so you get two results, one for sine 4 theta in terms of sine, and one for cos 4 theta in terms of cos. Okay, and then what you do is a cunning manipulation of the terms to put it all in terms of tan theta, or powers of tan theta. It's quite elegant. If you read the example from the FP2 textbook, which I reference in the assignment information, you'll see how to do that. And it's quite clever, quite nifty, but you can write tan 4 theta in terms of powers of tan theta in the same way. So that's the start point of using De Moivre's for trigonometric identities. It's the easier of two different things that you're going to be using it for to do with trigonometric identities. If you want to read on past the exercise to the next bit, feel free, but I will record another video on Wednesday to try and explain it, because it needs a little bit of careful explanation. It's to do with something that looks like that, or looks like that, where z is a complex number written in modulus argument form, that allows you, I'll tell you now, I'll tell you what it is. It allows you to write a power of sine theta, cos theta, or possibly tan theta, in terms of multiples of theta. So it's the exact opposite of this. The thing on its own will be like cos cube theta, and you'll be writing it in terms of multiples of theta. Have a read for yourself if you're interested, but I'll say more about that on Wednesday. For today, just try the exercise that I say about in the assessment, and hopefully you'll get the basics of how this all works. I hope that's clear. It's quite hard to explain, but hopefully you understood roughly what I was on about. Have a good day, both of you, and I'll speak to you again on Wednesday.